Buenas tardes. Bienvenidos al Seminario Fronteras de la Energía, organizado por el Instituto de Energías Renovables de la UNAM. En esta ocasión tengo el gusto de presentar a la doctora Signe Kjelstrup, de, de la Universidad Tecnológica de Ciencia y Tecnología de Noruega. Como cortesía a nuestra invitada, voy a cambiar al idioma inglés. Good afternoon, everyone. Welcome to the seminar of this week. I'm glad to present you the Professor Signe Kjelstrup. Before we start with the presentation, I will do some brief summary of the academic trajectory of Professor Kjelstrup. Professor Signe Kjelstrup has spent her entire academic career at the Norwegian University of Science and Technology, NTNU in Norwegian, in Trondheim, Norway, where she is currently Professor Emerita at the PoreLab Center of Excellence. She has also been guest professor at the USA, at the University of Barcelona, at at Delft in the Netherlands, at the University of Tokyo, and at ATH in Zurich. Her teaching and academic research has been done in the fields of physical chemistry, thermodynamics, non-equilibrium thermodynamics, electrochemical systems, and nanothermodynamics. She is co-author of the books Non-Equilibrium Thermodynamics for Engineering Applications and Nanothermodynamics Theory and Applications. Professor Kjelstrup is an elected member of the Norwegian Academy of Science and Letters, the Norwegian Academy of Technological Sciences, and the Royal Norwegian Society of Sciences and Letters, and was awarded an honorary doctorate at the Northeastern University of China, received the Guldberg and Wag Medal for the Norwegian Chemical Society, and received the Fridtjof Nansen Reward for Young Scientists. Professor Kjelstrup, thank you so much for accepting the invitation to participate with us in this seminar, and you may start with being a guest. Go ahead.
Thank you very much for this nice introduction. And I'm very glad to be here and was pleased with the invitation because I have very good memories from Mexico. I have seen your esteemed colleague Garcia Colin on one occasion, and that was on the occasion of a meeting in the Thermodynamic Society of Mexico, arranged by Professor Salazar. So I'm happy to talk to you. And the work I will report on is done together with Felix Schlums on my right-hand side here, and Øystein Gullbrekken in the center of the other picture. And the other co-authors are Sondre Schnell and Anders Lervik and Astrid Gunnarshaug. And the title of my talk is Modeling Electrochemical Systems Using Non-Equilibrium Thermodynamics. And the method of modeling is also my main project today. But I am talking about the important case, namely the lithium battery, and I hope you will enjoy seeing the results that come after in the end. So the backdrop is that more than 400 gigawatt hour has been proposed as production capacity for lithium battery cells in a year in Europe. This was in 2023. It has now been put on hold a bit, I think. Nevertheless, the battery is important because it is batteries are needed for energy storage. And why so? Solar energy and wind energy, they fluctuate over the season. So low power season must obtain energy from storage. And the lithium-ion battery is potential candidate. However, this battery runs the risk of thermal runaway. And thermal runaway means local hot spots in the battery, and it can put them, the spots can put the battery on fire, like we see in this little picture. You must have heard about that. So that is the backdrop of my talk. I'm looking at the lithium battery with particular interest to the thermal modeling. And this battery is interesting because it has the potential high voltage. That's the advantage of the battery. So the open circuit battery voltage is as high as 3.6 volt. And that electric potential difference, that comes from the energy difference of intercalated lithium in the two electrodes. So on the left-hand side, the anode, we have graphite and lithium metal moving up to the surface where the electrode reaction takes place. And on the right-hand side, we have lithium iron phosphate and lithium metal moving intercalated in this material. And lithium ion, which is formed on the left, is then consumed same amount on the right, and that completes the circuit. So the structure of the electrolyte between the two electrodes is a highly concentrated solution of a lithium salt, lithium hexaphosphate, that is. And here you see a snapshot of the electrolyte taken from molecular dynamics simulations. Here is the lithium ion, pink, and it can be surrounded by the phosphate ion, or together with the phosphate ion, screened by the negative ion. But it can also be screened by the solvent molecules, like in the upper left corner. The solvent molecules are ethylene carbonate and diethyl carbonate, and they can also screen the lithium ion. So, because of the carbonate group is also negatively charged. So this leaves us with two possibilities to describe the components in solution of the electrolyte. We have the neutral components, the neutral salt plus 3 diethyl carbonates, or we can choose a mixture of the single ions plus solvent. So normally electrochemical cell modeling takes place assuming a constant temperature. We then have typically the Nernst-Planck equations, where the transport of cations and anions, the difference between them, give us the electric current. So each ion is, the transport is driven by the gradient in electrochemical potential, and for the cation, it's defined here. It has the chemical part, and we have the electric part of the driving force. And not only the main driving force transports cations, also the anion force is active and has in principle a different transport coefficient. And the cell potential is determined from the open circuit potential, the delta phi at J equal to 0, and we subtract resistance losses in every part of the cell, and we subtract the anode overpotential and the cathode overpotentials. And these I view as resistivities of the cell, that the overpotential is related to the current density via the Butler-Volmer equation, where F is Faraday's constant, R is a gas constant, and T the temperature, and beta is a constant. So this is the common way, and temperature is constant. We use non-equilibrium thermodynamics to describe the thermal driving force and the thermal phenomena. So the way we do it, this systematic theory, I should mention first, was developed by Onsager, and it is now 100 years ago, so we could well teach it in the universities, this theory. It was extended 50 years ago by Bedot and Albano to deal also with layered systems, in particular with the boundaries, dynamic boundaries, like we have used a picture on the book to illustrate. So what the treatment for heterogeneous systems mean is that we write the entropy production for each layer in the system, and as well as for the surface between them. And for each thermodynamic phase, three-dimensional or two-dimensional, we write the flux force relations, and also connected with the fluxes and forces are the fluctuation dissipation theorems. They give you the transport coefficients for that particular case. So this systematic theory is now at the core of my interest. I would like to show you how it works on a lithium-ion battery, what it means for the 5 layers evolved, and I will also present some measured and simulated transport coefficients. This will be done somewhat superficially because of lack of time, but I need the values to show you what it means for the profiles of the electrical and chemical potential and the temperature also. And in the end, I will hope to show you there is an added benefit of using the entropy balance. Yes, here they are, the 3 bulk phases, the anode, the cathode, pink, and the electrolyte, yellow. There is only a plastic barrier where the electrolyte fills in. The surfaces are two-dimensional, I said, because they are treated by, the variables are integrated out the thickness of the surface so that they appear as two-dimensional, and I indicate that with this bar, vertical bar. So let us start with the equations. In the anode, in the graphite phase, electrons are the charge carrier, but and we can have electric current driven by the gradient in the electric potential and -1 and of, sorry, and the temperature comes in to define the driving force like this. But there can also be heat transport, and the measurable heat transport, this is why we have a prime here, is driven by the gradient in the inverse temperature. 2 products of flux and force, that's the prescription of Onsari. Now, from this 2 times 2 matrix of coefficients, I can write the variables I want to focus on, and that is the heat flux and the electric potential gradient in the layer we are now discussing. And the heat flux has not only a contribution from Fourier's law, a Fourier law type contribution. Here, lambda is thermal conductivity, but it also has the possibility for reversible heat transport, and that is expressed by the Peltier coefficient. And since the heat transport is reversible, we interpret it in terms of transported entropies, and here is the interpretation of the model for PI. It is heat transport in the absence of temperature gradients. And the Peltier heat contributes for symmetry reasons to the electric potential gradient. So you see immediately the effect of such a gradient. And of course, there is a ohmic potential drop. Kappa is the thermal conductivity, electric conductivity, I mean. The lithium metal moves to the electrode interface here, where the reaction takes place. It moves as a metal. And if there is steady state, it must be supplied at the rate of the electric a chemical reaction or the electric current density. And this diffusion could be rate limiting, and that then creates a concentration gradient dependent on the diffusion coefficient of the metal in the phase. Sorry. So from the concentration gradient, we can compute the gradient in chemical potential of the lithium metal in the graphite. But only if we know the thermodynamic factor, which describes the non-ideality of the component in the phase. So these are the governing equations for the anode, and there is a similar set for the cathode phase where lithium also intercalates. The surface system is constructed with Gibbs excess properties. To explain a little bit what that is, I have first taken the Gibbs equation familiar for homogeneous phases. Here you see the time rate of change of the entropy density expressed by the internal energy density variation and the concentration variation. Now, this is for a one-dimensional transport used in on a continuous form like this. For the surface, we integrate out the extension of the surface, and inside we have for all variables a density variation, which gives you eventually for the entropy a surface entropy, a surface internal energy, and surface absorption. And we even have a particular temperature of the surface belonging to this layer, because we assume that Gibbs equation now applies also away from equilibrium in the total cell. It applies for the surface and defines local equilibrium there. And here, of course, there are additional terms due to the chemical reaction. So if I now was going to construct the surface excess entropy production, there is no longer only one term for the heat flux. There is the heat flux into the surface, driven by the inverse temperature of the surface and the incoming bulk phase, and a similar term for the outgoing heat flux. There can also be adsorption of reactants and desorption of products written in the same style with a delta, meaning a discrete difference. And at the surface, it is an electric potential jump that counts, and that is a scalar, and it connects with the reaction Gibbs energy when the electric current density is proportional to the reaction rate. And you see immediately that if the entropy production is zero, it means that there is constant temperature throughout and equilibrium for adsorption and desorption. And here you find the electric potential jump given by the reaction Gibbs energy, and that is now the Nernst equation. So the Nernst equation is contained in this formula. And I'm going to use a simplified version. I keep the two heat fluxes into the surface and out of the surface, and I assume equilibrium for adsorption and desorption. And here is the last term I just explained. So the formula will give us 3 times 3 sets of equations. And I will interpret the resistance of the surface like I did before with the Butler-Volmer equation. And here is now the Nernst equation for open circuit potential conditions. And we find that the surface electric potential jump not only has the 2 contributions from Gibbs and energy and the ohmic potential drop, there are also two contributions from the thermal driving forces being non-zero. And in addition, I can use the flux equation. This is not shown, but I can find the net Peltier heat effect of the surface. And there is such a net effect because the entropy flux in is different from the entropy flux out. After all, there is an entropy production. And these fluxes can, reversible conditions, be replaced by the Peltier coefficients, and the reaction gives entropy, that is. So this is now the interpretation of the reversible heat transport in the electrolyte. And finally, we have the entropy production and the flux equations for the electrolyte. And you see that we have two components now being transported, in addition to the thermal driving force and the electric driving force. So we have a set of 4 fluxes and 4 forces, and they are related by a lot of coefficients. And let us only look at the bottom line here. The Peltier term comes in as it did for the electrode, and then there are contributions from gradients in the salt, lithium hexafluoride, that is now, and from the co-solvent, diethyl carbonate. And the TL and the TD are transport numbers, and kappa is the conductivity of the electrolyte. So these are the governing equations that I can integrate across and find these unknown variables on the left-hand side, provided I know all the coefficients. And that is a pain, because there are so many coefficients, but we have now, we think, all of them for this particular system. We have measured the Seebeck coefficient to provide the Peltier heat. We have simulated diffusion coefficients and thermal diffusion coefficients using molecular dynamics simulations. So here is a measurement of the Seebeck coefficient. We have the electrolyte sandwiched between 2 electrode layers where the reaction takes place. And these are again in contact with copper on 2 sides, and the copper is heated by hot water or by cold water, and we measure the resulting electric driving force, delta phi, and we plot it versus the temperature difference, and the slope is now my Seebeck coefficient, and thanks to the wonderful symmetry of the Onsager matrix, we find the Peltier heat from this identity. And even if the Seebeck coefficient is only 1 millivolt per Kelvin, it's surprising, but it represents 35 kilojoule per mole of heat. And the minus sign means that the anode is warming up when you discharge the battery. If we wait hours, we will eventually find out that the temperature difference stays constant over the hours, but the electric signal will show a small reduction after some time, or depending on how big the temperature difference is. And this small reduction can be used to find other terms in the entropy balance for the electrode, and but the deviation is small, and we will neglect the Soré effect. This is underlying this observation here. Yeah, so what more do we need to do the calculations? Equilibrium values for the thermodynamic potential for the and chemical potential, I mean. And I repeat the equation I used before, where the thermodynamic factor describes non-ideality of the solution. In the more normal for chemists is to use the activity coefficient, I think, and that looks for a system with more components like this. So the gamma is now the activity coefficient that normally multiplies the concentration. But this relation is clear. It gives you for an ideal solution the value of 1 for the pure component, and for the interactions between the components, the thermodynamic factor is 0. And the value is easily obtainable from particle fluctuations, and that those are standard in solution theory. And we have shown a method which gives them in even for small system, provided you make the scaling law for the small system. So we are approaching. I have told you that there are 2 ways to describe the electrolyte in terms of ionic components and solvent, or in terms of neutral components and the electric driving force directly. Now, we shall use the top set of equations to simulate molecular dynamic simulations, simulate all the coefficients, and the bottom set, because that is more and better related to the measured variables. For instance, the gradient in electric potential for the lithium electrodes, that is present here, but not here, so it is hiding. But the 2 formulations are, of course, related, because they both describe the same entropy production. That is an invariant quantity. So the procedure for coefficient determination is that we find directly from velocity correlation functions of the ions in the molecular dynamics box. Then we find the coefficients lambda ij. But we don't want the wall frame of reference of the box, because that gives us so many coefficients. We can eliminate one of them by choosing EC as a frame of reference instead of the wall. And that gives us the coefficients that have superscript indicating the charge interaction. And from the relation between the driving forces and the others, we obtain the measurable heat fluxes. So now it's time to look at the results. Here are the measurable coefficients, and we see immediately that all of them are same order of magnitude, and none can be neglected. And this is exactly what we can use the relations for. If you go along with all coefficients, you get these numbers for the transference coefficients and the transport number, 0.3, conductivity, etc. But if you start introducing assumptions and neglect, for instance, anion-cation coupling, then you get very different numbers with respect to preciseness. And even more so, if you start to use self-diffusion coefficients. So you need to use the full set of coefficients. But now we have them, and we can compute. We have 3 unknowns and 3 known, 3 equations to find them, and the rest are known. So we can compute all the contributions in the electrolyte, that is, to the electrochemical, to the electric potential. So here, this whole black line describes all the contributions, and you see that all terms are sizable. None of them can be neglected. And the first time we looked at it, the problem, we could only estimate the thermal contribution to the electric potential gradient, and the data from some aged cell indicated that there was indeed a sizable gradient. This gradient here produces a thermal polarization of the same order of magnitude as the salt, but it is dubious, this measurement. It is, of course, terribly difficult to measure on location inside the battery. And maybe the model is more reliable if we have reliable data. This data also shows that the chemistry plays a role here and could be used to reduce the polarization significantly. So here is the electric potential profile across the cell. So if you look at the open circuit potential, the difference between the 2 poles are approximately 3.6 volt. And this is reduced, this difference, once you pass current through, typical for battery discharge, and then it becomes 3.2. For practical purposes, the temperature is constant. But if you now zoom in, you see that the temperature in the anode surface is a little bit higher than the surroundings, and the temperature in the cathode surface is a little bit lower. So the equations are, the results are reflecting the equations that we have, that here was a warming effect and here was a cooling effect. So this may not be so interesting because it is small, but if we now look at the heat flux across the system, we see very interesting things. In the electrolyte, it is a large and positive value. And in the anode, it's clear that the heat flux goes out of the system from the electrode surface and out. And similar on the cathode side, it also has the same direction. It goes to the side which is cooled to compensate for that. And we see the Fourier type term does dominate. The Fourier coefficients give a small contribution, as I told you, but the Fourier heats are sizable. So, and they show that you should not believe that there is no heat flux if the temperature gradient is 0. This will be there always. The chemical potential gradient contributions show also here very clearly that the gradient is negative, meaning that there is accumulation of the lithium salt on the left-hand side of the electrode, on the left-hand side of the electrolyte, and here it's positive, so the diethyl carbonate is accumulating on the other side. The other terms, again, the anode, the Fourier coefficient terms are small, but the contribution from the other component is significant, and so is the contribution from charge transport. So we are wasting work in the electrolyte by these movements, and the chemistry could be designed to take care of that, I would think. The accumulated entropy production is a measure of how much we lose in work without gaining anything. And here you see a very clear message. The electrolyte is so much more important than the anode and cathode bulk phases, that is. But if we look at the figure, we see that still the surfaces are even more dominating than the electrode contribution, which is here. So this is, of course, important to know. But can we use the entropy balance for something more? I wonder. So in the steady state, the entropy production that we obtain from the local flux force pairs, if we integrate that from the incoming to the outgoing flux across all the 5 layers, this should be equal to the entropy flux out minus that in. And not only does it hold for the total cell, it should hold for any layer. So my question is the left-hand side equal to the right-hand side for my model? Now, that is a crucial test, an acid test. And yes, it is. Look here for the electrolyte, entropy flux difference is 5.75, exactly equal to what you obtain when you integrate. And so it goes for the anode and cathode surface and for the total cell. And now there is a conclusion you can make. Your model is in agreement with the second law of thermodynamics. Wonderful conclusion, I think. We can use this equation to sort out what is thermodynamically sound and not. But we see also something else. I have not said it, but all the time when I have integrated that across, I have held the outside temperatures at 290 Kelvin both. But if I now make a slight change, you see there is a dramatic increase in the electrolyte waste of energy, dissipation of energy, that is, or lost work. And you obtain almost the same for the electrode surfaces. So the reason why it almost doubles for the total cell must be that now the bulk anode and cathode counts. So here we have a tool to examine really how the cell is losing work in operation. And here is a test we have done on typical ways to model heat phenomena in the cell. Here is our model in red, and RHE means reversible heat effect, and some people make an average value across the whole system out of what we know for the total cell, and some people neglect it altogether. And both these models do not obey the second law, so they better improve. Final comment, we have reached at the battery stack performance. After all, so far I have been talking only of the single cell. Now, in reality, the battery is stacked with many, many cells. And here is the single cell with the anode and the cathode that I have been talking about. And here is the row of neighboring cells. So what happens if I solve the temperature profile during charging of the battery? During charging of the battery, at initial time, before the steady state is reached, you see the cooling of the anode and heating of the cathode here down in the left-hand side corner. Now, it is opposite of what I said before, but remember, now we are charging the battery again. It's not in the configuration we used it before when it was producing electricity. So we are charging, and we can see the effect of the Peltier heats. But as time goes and heat accumulates inside, the peaks become blurred, and eventually they will reach a steady state. And here, with 4 cells only, there is a negligible rise in the temperature. But here, when you have 80 cells, then after 100 seconds, we are here, but after 400 seconds, we seem to have arrived at a steady state. And this temperature is more than 8 times above the temperature on the 2 sides that we started with. So this could possibly lead to hotspots if the cells are not joined in perfect position, or if they are aged and structure inside is awkward for some reason. So I think this is a very interesting possibility we have to find out more about the performance of the battery. So now it remains for me to conclude. I have reported to you, however, a bit briefly, equilibrium and transport properties, and applied these properties to describe battery performance. The details are found in the articles, especially in the JAX article we wrote on the topic. I have tried to show you that non-equilibrium thermodynamics gives you a systematic handle on the description of this battery, and I think electrochemical cells in general, it could be useful. Electrochemical systems are always layered and difficult to deal with the electrode. The theory of non-equilibrium thermodynamics allows us to use fluctuation dissipation theorems directly to give transport coefficients. And you can also measure directly, for instance, I showed you the Seebeck coefficient, to get at a more difficult parameter, the Peltier heat. And I showed you that it's not so in this with this electrolyte that some coefficients are small. We actually need all of them for precise modeling of thermal effects. And then as a side benefit, I talked about using the entropy balance for the benefit of modeling. I think it is an underused opportunity. Thank you very much for listening, for your attention. I thank also my own Research Council of Norway for granting PoreLab Center of Excellence, and the program that made all the calculations of the profiles can be found at GitHub with this address, and I will be happy to answer any questions. Thank you.
Thank you, Professor Kjelstrup, for your presentation. So we start with the question sessions. You may raise your hand in Zoom and ask the speaker directly. You may write it down in the chat group here in Zoom, or if you're watching on YouTube, you can write in the chat box in YouTube and we can pass the questions to the speaker. So we start with Professor Mariano. Go ahead.
Hello, Signe. It's a pleasure to see you again.
Oh, hello, Mariano.
I apologize because I had to come in later because I was teaching, but I came in just 4 or 5 minutes after you started talking. But anyway, I'm very glad that you exposed so neatly the benefits of non-equilibrium thermodynamics. And my question has to do with the following. Apparently, these cells should have some non-linear contributions. You have stuck to the linear version of irreversible thermodynamics. Can you comment on that?
Of course. Yeah. If you look very closely, I had one nonlinear version, the Butler-Volmer equation.
Yeah.
But I did not relate that directly to the flux force relations. I used it to interpret the electric resistance of the surface. It is a phenomenon related to the surface, and it is always dissipative, and it is always reducing the voltage drop there, the work you can get out of it. So I think there is some justification for doing exactly that. But on the other hand, we are, it seems to be sufficient with linear version. Otherwise, yeah.
Yeah, okay. Yeah, well, I find that amazing because it's a highly nonlinear problem. But anyway.
It maybe the division of the layers make it differently.
Yeah,
because
probably.
Locally the gradient is not so big.
No, but you have still 40 Kelvin over, I think it was 100.
Yeah. Locally the gradient can be big.
Yeah.
No, so we have always put an emphasis on the validity of local equilibrium. Of course, I assume that for the Gibbs equation that it applies for the electrode, for the excess variables.
Yeah.
We have some evidence that it applies for evaporation and condensation.
But
anyway, of course, yeah.
No, anyway, it's not. In fact, I'm impressed by the fact that you can describe what's going on. And I agree that the inclusion of the Peltier coefficient is crucial for whatever you want to do on that system. And the other question I had to do with who measures that? I mean, you measure the Seebeck coefficient. Or do you do it, or do you rely?
Yes, I do it. Yeah, I have some. Yeah. Well, the student is doing it.
I know, but it's your group.
Astrid Gunnarshaug did it in her PhD.
Okay. Well, say hello to Dick on my behalf, and again, I reassure you that it's a pleasure to see you, and thank you for giving a very nice lecture.
Thank you for coming to my lecture. I say hello to my friends.
I will.
Bueno.
We have a question in the auditorium, so go ahead.
Sí.
Tenemos una pregunta en el auditorio, adelante.
Okay.
Hello.
I don't hear anything.
Thank you so much for your presentation. It really brings my interest into this this type of thermodynamics that really you don't understand. You cannot understand the electrochemistry from the physics point of view. But with this theory, you can much better. And I've been working with the lithium-ion batteries for a while. I was wondering, in this approach, where would you consider the formation of these solid electrolyte interfaces or the cathode electrolyte interface in terms of the entropy formation terms?
That is a very crucial question. Thank you for formulating also the importance of the analysis. I think the very last picture where I showed the table of the entropy production being the same whether you computed it from the integral across the electrolyte or from the entropy fluxes, that indicates that there is something on the cathode which is not giving you a normal entropy we try to describe it in the paper we are now writing. It is not the entropy of lithium is about 30 joule per Kelvin and mole. It is a much larger value. And we wonder if it is an indication of a phase transition of lithium in the confined pores of this lithium iron phosphate lattice, you could say. So the numbers indicate that there is something there that is more needs to be done, simply. And I don't know if that answers your question well enough, but you can't really do the easy analysis of the anode so easily on the cathode side. The cathode is special, yes. And you can learn about this by imposing on the cathode side the entropy consistency modeling. Then you can force it to obey this balance equation and see what the entropy would become. Yeah, I'm not expressing myself very clearly now, but there is more to be done. That's the bottom line here.
Yes, but this, I think, these changes in the temperature that they show, the entropy formation might be. So I will be following this paper in progress. Thank you so much for your answer.
Thank you. And it is also maybe written more of it in the paper with Gunnar. Thank you.
Thank you. Anyone else? Go ahead, Doctor. Okay, so first, sorry, Dr. Sergio, first Dr. Ramos, and then you next, okay?
Sure. Okay, thank you very much for your presentation. And I don't know if I followed the description correctly, but if I understood correctly, the model cannot explain the sharp rise in temperature that leads sometimes to fire. And this, I think that you attributed this possibility to the formation of hotspots due to some other mechanism or some other phenomenon. Am I right?
Yes, I did not touch upon any mechanism for fire, and I may have been stretching the idea too far to say that knowledge of the temperature alone can explain how this fire arises. What I meant to imply is that knowledge of where the heat sources and sinks are, that can change in particular with aging of the whole system. With the materials aging, you can also have fractals when depositing the metal and taking it out and making resistances change dramatically if things become too close and too far apart, and all these things. But now we have a tool we can play with. We can use, we can see what happens if we change the thermal conductivity, if we increase it by some aging. I think it will always increase by aging. We could find the limit value it need to be below or something. So I wasn't pinpointing any origin of the fire, no. But I don't know, please correct me. It is also, there are reports that these batteries take fire more easily.
Well, as far as I understand, I'm not a specialist, but as far as I understand, this is the big problem of these lithium-ion batteries. Okay.
Yeah.
Well, thank you very much.
Mhm.
Doctor Sergio Cuevas.
Thank you for the nice lecture, Professor. My question is related with the entropy production. I would like to know if you think that is it of any interest to try to optimize the system using this tool, the entropy production, as is done in some other problems in engineering, and so it has any sense in this case to
Of
try to
course,
use this?
I think you are completely right. I think it makes very much sense, and I tried to indicate exactly that. And the first step in that direction is to know where are the losses and what is the cause of the loss. But of course, you should try and avoid them as much as possible, and like you do in process industry, and this is part of what I mean when I say that this is an underused equation. It is maybe an underused opportunity to investigate. Because when I see books in chemical engineering, I don't find much about the entropy balance. Everybody knows how to solve systems with the mass balance, the momentum balance, and the energy balance. But there is a whole equation here missing, underused.
Okay.
It is not missing, of course, but underused is a better word.
Okay, thank you very much. Thank you.
Thank you, Dr. Sergio. Iram Hernandez, you have a question?
Hi, thanks for the lecture, Professor. In the slide 25, I see that some electrolytes don't have a thermal polarity. I don't know if that's correct. The question is, why don't see this effect in those electrolytes? And
Which page was it?
25.
25. Yeah, I have to move. So I see.
And the other question is that if we have this effect variation of the temperature
Here.
Yes, of course, thermal polarization. I don't see two values. The question is,
You don't see
in electrolyte 37 SESC, the values of the table.
in the table, you are speaking about these numbers here, 34.4, and they come by introducing the pi, which is negative here, and using this number. So it is just an estimate.
But in all the
These
electrolytes,
are computed from the isothermal electrolyte, and then this was our first step in this direction. But the next slide, then we solved the total system with all with the thermal polarization included. Here, that is for the whole system, but
So-
this was only an estimate to see what does it take to give a term similar in value as the polarization by the salt. So there was we took some data from the literature here to see what the number would. When I explained it, I also said that I doubt these measurements because it must be very difficult to measure on location inside the battery.
all the electrolytes have this phenomenon.
All the electrolyte, this is, I don't, can you please repeat what you said?
Sorry, there's a lot of noise here. All the electrolytes have this phenomenon of the thermal polarization.
Yes, in principle, the term is there, but it is smaller than this one.
Thank you.
Mm. You will
Okay.
find it in the archive manuscript. What we not this estimate, but only the calculated value.
Thank you. Iram, if you have any other question, because there is a lot of noise in your surroundings, you can write it in the chat, okay? So, okay, any more questions?
Thank you.
I have a question about it caught my attention that you put the thermodiffusion effects in particular, Sorad effect is negligible in the model, right?
Mm-hmm.
Is there any physical reason? Is the measurements of the coefficients compared with the thermoelectric effects are much smaller, or is only
Yes,
a matter of mathematical?
I think the Soré effect is poorly understood. So it describes the ability of components to carry heat reversible in the absence of electric current. So it is in a thermal field, the thermal field will be able to separate components, and it is this effect that is the Soré effect. So when it is small, it only means that it's very difficult to separate, to reach any separation of the components in the thermal field. And you may believe that the two solvents, the co-solvents, the carbonates, the organic carbonates, are difficult to separate in a field. But you could think that maybe the salt is that much different from the other, that they will separate. So that's an application of waste heat for separation. And that is the Soré effect.
Okay,
That is, I'm afraid, only superficial thing I can say.
okay, so I was wondering if taking into account the role of diffusion with the thermodiffusion effects, Sorad or Dufault, can give an explanation or enlighten an explanation in the why the deposits of salt.
Yes, I think it can. In fact, I also have these data, but I decided that there was no time to show them. But I added them here. So we also computed, no, I have not included the thermal diffusion. These are only diffusion coefficients.
Okay.
Yeah. But we also have measured this separation and tried to compute the heat flux. And that is in the JAX paper. So it is, they are there, but they are small.
Okay. Well, thank you very much, Professor. So we have time for one more questions, or okay, if not, so we thank Professor Signe Kjelstrup for accepting the invitation to participate in this seminar, and thank you all for your